Good morning to all of you. I welcome you to this session of Big Data Analytics. In today's session, we are going to discuss about Hdfs Architecture. So we'll begin by discussing the block size in Hdfs. Okay? We'll discuss about the block size in Hdfs. So as we have discussed, the block size in Hdfs is quite big as compared to other file systems. For example, in our Windows system, we have a block size of 4 KB to 8 KB. Even in our Linux systems, we have the block size similar to that of Windows, that is 4 KB or 8 KB. Okay. But in Hdfs, as we have discussed previously, we have big block size. Okay. Either 64 MB or 128 MB is the default for clusters. Okay. So block size, as you know, is the smallest unit of data. Okay. Is the smallest unit of data that a file system can store. So if you have a block size of 64 MB, that means a file as small as 1K or a file as big as 64 MB will take up one block. Once you cross the 64 MB, you will need a second block. That is the concept about these blocks in Hdfs. Now, you may ask, what is the advantage in doing that? Okay. So you see, Hdfs is meant to handle large files. We are not talking of small files, okay, 1 MB, 10 MB. We are talking of dBs and GBs and extra exabytes and all, right? So if you have, say, let's suppose you have a 1000 MB file, okay, with a 4K block size, you would require 256,000 blocks, or in that sense, 256,000 requests to get that file. Because one request per block would be there. So this many number of blocks would be there if your block size is small, say 4K. Now, if you have a block size as 64 MB, okay, in that case, you will only have 16 requests. Okay. So in that case, you see your name node is loaded to a lesser extent. Okay. There is lesser traffic around, okay, and you can read your data at a streaming pace. So that is the idea behind picking up a huge block size for Hdfs. Okay. Also, you know that Hdfs design was originally inspired by the GFS. You remember the Google file system, the white paper that Google wrote to take care of the storage and the analytic problems for huge files on its servers. Okay. Even if you see its terminology, okay, in the original GFS paper, we have terminology like chunk, which means a block. Okay. Chunk server means a data node. Master, which means a name. Okay. So we are talking of a chunk size of 64 MB. Okay. So chunk refers to the block. Okay. So a large chunk size or a large block size offers several important advantages. So we can discuss them one by one. First, it reduces clients' need to interact with the master. Okay. Right. So the number of requests are obviously limited, but here the clients they don't need to interact with the master frequently. They just request once while the file is to be written or read from the cluster. Okay, only one initial request is there, and it will decrease the workload of the name. Second, on a large chunk, a client is more likely to perform many operations. So you see, a large chunk, many operations can be there. So if the more is the number of chunks or blocks, then more network traffic will be there. So we can reduce the network overhead by taking a large chunk or a large block. Okay. And most important, it reduces the size of the metadata. So information about each block is to be maintained by the master or the name node. So if it needs to maintain information or metadata about thousands of blocks rather than hundreds, it would take up a lot of memory and time and would slow down its working. So a large chunk size reduces the workload on name node, okay, and lesser metadata needs to be stored, so it's giving it a faster access. Now, how do we calculate, the block size? How it is calculated by Hadoop? Okay. You see, if the default block size is 128 MB, then if you split up a file into blocks, all the blocks, are of the same size except the last block. I hope you understand this thing. Whenever you split up a file and say the block size is say 64 or 128 MB, then the splits would be of the same size except the last split or the last block, which would be either the same size or small. Okay. So let's just let me just elaborate it. Yeah, it's here. Say I have a 530 MB file. This is a file of say 530 MB which needs to be stored into the HDFS. So if the block size is taken up as 128 MB, as you can see here, then you divide this 530 by 120. That is how blocks are calculated. You do this calculation. Okay. So 128 into 4 is 512. Okay. So you have 4 blocks of size 128. That adds up to 512 MB. And the last block would be of size 18 MB. So you can read this point here that when a file is split up, all blocks of the file are of the same size except the last block, which may be the same size. Okay, the last block could be also 128 MB, but in this case it is lesser. For example, if I take a file of size 512 MB which needs to be stored in the cluster, okay, in this case we will have 4 blocks of 512 MB. Sorry, 4 blocks of 128 MB, so that it adds up to the file size. So here in this case we have all the blocks of the same size. So I'll just elaborate both the things here so that you can understand it. Important is how the block size is calculated. I can just put it here, and I can write here a file size as say 540 MB. And if you divide 540 by 128, you get 4 blocks like this and 1 block of 22 MB. So you can see both the scenarios as are listed here in this point. Should be clear how you split up. Okay, I think it should be 28, right? Yeah, 28. So this is how block size is calculated in HDFS by HDFS to store the blocks of files in the cluster. Right. Next, we discuss about block reports and heartbeats. Okay. 2 things that are done by data node frequently is to send number 1 heartbeats to the name node and block reports to the name node. Okay. So you can write that this is done by data nodes. Okay. So each data node is sending a heartbeat to the name node and a block report to the name node. Since name node contains the metadata of the entire cluster, it contains the detail of each folder, each file, whatever is the replication factor of the cluster, what are the block names, block IDs, etc. All this information is in the name node metadata. Okay. And it is also storing the information about the location of the blocks for each file. Okay. Where the blocks of a file are located. Okay. Now, data nodes, they store the following information. First, you see what is stored by name node is metadata and what are its constituents. You have seen what all is there in the metadata. Then data nodes, they are storing the actual data. Okay, data nodes are storing the actual data, and they store it in conjunction, in consultation with name node all the time, so that they can get the block IDs and which replica to be placed or which block to be placed on which data node, right? And metadata for the data stored in the blocks. You see, data nodes are taking care of 2 things. Note it very carefully. First, they are storing actual data. Then there is some metadata about this data also. Okay, so data node also stores metadata for the data that you have stored in the block. Okay. So this metadata, mainly contains checksums. Okay. It contains checksums for the data stored in the block. Checksum is something which would, which would fulfill the validity of the data in the block. If you have a corrupted block, okay, or if you have picked up a block for storage from an unknown source and maybe it is corrupted, its checksum would vary from the original data. Okay, so it's important for a data node to first calculate the checksum, okay, and store it in the data node itself along with the actual data. So every block has got a checksum file associated with it. Okay, so I write here every block has a checksum file associated with it. Okay, we call it the .meta file. It has got the extension .meta. Remember, and we'll see how this checksum is calculated and where it is stored. So every block has a checksum file associated with it. Every block. Okay. So if you have got 100 blocks stored in different data nodes, then there are 100 checksum .meta files. That is files with .meta extension, indicating that this is a file which contains the metadata about the actual data. Okay, I hope this point is clear. What is the functionality of data node? In addition to doing this, okay, they send heartbeats and block reports to the name node periodically. That is after a fixed interval of time, as set up by us in our configuration. They'll be sending something known as a heartbeat and something known as a block report to the name. Now, this heartbeat indicates that this particular data node is active and alive. It is not dead. It is functioning properly. Okay. So this interval of heartbeat can be set up by this property in Hdfs site.xml file. Okay. If you don't set this, by default it is 3. By default it is set to 3 seconds. Every 3 seconds, a heartbeat or a signal, heartbeat is a signal, is sent by the data node to the name node, by each data node to the name node, indicating that it is active and alive and is working properly. Okay. Now, what information is sent in this signal? Like I say, a heartbeat is sent or a signal is sent, indicating that the particular data node is active and alive. What it contains, what information is there in it, you can see on screen now. It contains the registration information of the data node. It contains the capacity of the data node, the total storage capacity available at the data node. Okay. It also tells the distributed file system used. That is the storage that has been used by HDFS till this point. The storage that is remaining. Okay. The block pool that has been used. Okay. Storage used by the block pool. So you see there is with every file, if a file has got say 100 blocks, then there is a block pool for that particular file. It will also occupy some storage. So that information is also there. Then number of transfers from this data node to others. Okay, this is a property known as X-bits in progress. Okay, that means how many transfers have been made from this data node to others. Okay, then number of active transceiver threads received. So this is something internal. I'm just referring so that you can understand what all is there in the heartbeat. We don't need to look too much into this. Just we should know what is there in the heartbeat. Okay. Then X-bits in progress, that is number of transfers that are in progress. Then what is the cache capacity available at the data node? What is the cache that has been used so far? Okay, this is all there in the heartbeat. That is a signal sent by a data node to the name node. By default, every 3 seconds. If you want to increase it, you can do that by setting up this configuration property value and setting its value to whatever you want to set it in seconds. This is in seconds, right? Now, what does the name node do with this information? What does the name node do with this heartbeat information? It will first of all know the health of the data. Okay, by looking at all these things. Like for example, the first thing is that heartbeat is not sent. So if a heartbeat is not received by name node from data nodes, from several data nodes, then name node will think that these data nodes are dead. So what it will do, whatever data is there, the blocks are there, it would pick it up from its replicas on other nodes and transfer to some new data. Okay. So if the heartbeat or the signal is not sent, then that data node is marked as dead. Okay. So other things is like if the name node sees that the total storage capacity is almost nil. Okay. Even then it will mark that no more data should be sent to this data node, number one, or it can transfer several blocks from this data node to some empty data. Okay. So when we say what this name node does with this information, the first one is it can see the health of the data node. Okay. Then it can also see its registration information if it's a newly added data node. Okay. Then update the matrix of the data node. Okay, the information sent in the heartbeat is used for updating the matrix of the node. Okay, this information can help us to issue certain commands to data node. Okay, right. Then the name node can issue following commands to data node based on the information received in the heartbeat. So what commands can be issued? We can see that block recovery command. Okay, like if the node is not working. Okay, if the node is not working, then we can recover the blocks which were there on this node by taking it from their replicas on other nodes. Okay, and then the block command is there, the cache and cache command is there. Okay, so you can cache or uncache the blocks if there is some memory issues. So this is regarding the heartbeat. Okay, this is done frequently, periodically at an interval of 3 seconds by default. Trying to keep that in mind. Next is the block reports. Okay, so interval of block report is determined by this configuration parameter dfs.blockreport.interval msec. Okay, and by default it is in milliseconds. The value is in milliseconds, and the setting is in hdfs site.xml. So by default, a block report is sent by the data node to the name node every 6 minutes. Okay, this is milliseconds. This comes up to 6 minutes. You may increase or decrease this number, but this is the default 6 minutes. I'll write it here. The default is 6 minutes. So after every 6 minutes, a block report is sent from the data node to the name node. Now, what is the information there in the block report? The information is about the registration information of the data node. Okay, and the blocks which are there. You see, blocks in a data node keep on changing. If you remove a file from the cluster, if you add a file to the cluster, okay, then the data node information keeps on changing. So this information is sent every 6 minutes to the name node. This information about blocks is the block ID is there, the block length is there, block generation timestamp is there, state of block replica is there. Okay, state means, for example, if the replica, whether it is being finalized or it is waiting to be recovered. Okay, I'll discuss these two things pretty soon with you in today's session itself. But what is this finalization and what is this waiting to be recovered? Okay, so all this information is sent in the block report. Now, what does the name node do with this information? Okay, let's see. So, if it is a first time report, like if this is the first block report sent up by this data node to name node, okay, it will simply add up all the valid replicas that are present on this name node. Okay, it will ignore the invalid blocks till the next block report. Okay. Now, if this node is already registered with the name node, okay, then it will update the block information, like what blocks are there. It will information this block information on its metadata. Okay, and the newly blocked report is compared with the old report, and information about successful, corrupted, invalidated blocks is updated. So we'll soon see what are these corrupt blocks, successful blocks, what are these replicas, that we'll see when we actually work with them in the cluster in today's session, right? So this is regarding the block reports and heartbeats, very important, for the functioning of the cluster, right? So next we move on to the FS image and edits files. Okay. So I discussed with you in my some of my previous discussions that your metadata of the name node is stored in a persistent file, a file which exists on the storage of the cluster, and that file is known as FS image, or it stands for file system image. So file system image means the file system metadata is there on the FS image file. There is another file with the name of edit logs. Okay, there is another image, another file with the name of edit logs. Now let's see how the name node it persists file system metadata. For example, as a user, if a user gives a command of creating a directory, okay, then first of all, this request goes to the name node to check on which data node this directory could be created. Okay, so this information is there. So as we discussed in our database management system when we were discussing how data is stored, okay, Then we discussed that two types of schemes are there. That is the immediate update and deferred update, if you remember. Okay. So similar to here, like the FS image file is not dealing with the data directly. Okay, FS image file, which is a permanent file which contains the file system metadata, it does not interact with your file system commands directly, your updates directly. Instead, there is a series of edit log files. There are many edit log files which store whatever changes you make in your cluster. So I repeat, there is a FSMH file and there are a series of edit log files. Okay, the changes that you make in your cluster are stored in the edit log files, and after a fixed interval of time as specified by you in the configuration, these files are merged. The edits file is merged with the FSMH file to get an updated FSMH file. Okay, this process is known as checkpointing. Okay, this process is known as checkpointing. So you see, HDFS metadata changes are persisted to the edit log. First, whatever changes are there in the cluster, they are recorded on the edit log. They are not directly recorded in the FSMH file. And then after a fixed interval of time, the edits file and the FSMH file are merged to get an updated FSMH file, and your edit log file is again blank. Okay. So you see, at a high level, the name node's primary responsibility is to store HDFS namespace or the metadata. So what does that contain? The directory tree, file permissions, and the mapping of the files to block IDs. Okay. So it's very important that this is safely persisted to stable storage. So whatever changes are being made in the cluster, they should be stored in the FSMH so that we have an updated FSMH file with us. Okay. So the metadata you see is stored in two different constructs. Okay. Whenever you start working with your cluster, you have a FSMH file which contains the current status of your cluster and a blank edit log file. Okay. So FSMH is a file that represents a point-in-time snapshot of the file system's metadata. Okay. Now, this FSMH is a very good file, very efficient to read, but you should not be making small changes to it. Okay, because if you keep on updating it on a regular basis, your cluster working would become slow. Okay, so rather than writing a new FS image every time the namespace is modified, I think I've made my point clear. Like if there is any update in your cluster, rather than writing it to your FS image file, that is making the changes to your metadata in FS image, the name node instead records these operations in the edit log file. Okay, so and then we have a series of such files. Okay, there's not just one file, there are a series of edits files. Okay, and the time from which you formatted your name node and you started your cluster, all the edits files are there, so that if your name node crashes, then you can recover some data from these edits files, edit segment files. Okay, I'll show you these files soon. Okay. So this is checkpointing. Okay, merging of the FS image and your edit log files is checkpointing. Okay, so checkpointing is the process that takes an FS image and edit log and compacts them into a new FS image. Okay, it merges these two files into a new FS image. Okay, so name node can work properly with this. This is an efficient operation and reduces the name node startup time. And this process is taken up by secondary name node. Okay, this checkpointing process, that is the merger of your FS image and edit log. This is the responsibility of the process secondary name node. So as we discussed when we were discussing the distributed file system daemons, you would remember that we said that secondary name node is assisting name node in certain operations in certain housekeeping jobs. Okay, so that is one of the jobs. The checkpointing of this merging of this FS image and edits is done by your secondary name node. Okay, so you can see here FS image and edit log, the contents are merged to get a new FS image and updated FS image for your cluster. Okay. Now, two properties they can trigger this checkpointing. Important. There are two properties which can trigger this checkpointing. One is if the dfs.nameNode.checkpoint.period. Okay, so I told you that this is what 3600 seconds. Okay, dfs.nameNode.checkpoint.period. This is 3600 seconds or 1 hour. So this checkpointing by default is done every 3600 seconds or 1 hour. You may reduce or you may increase this time by taking this dfs.nameNode.checkpoint.period property. Okay. And similarly, another way is like if the number of transactions in your edit file they exceed, the number of transactions you can set. So dfs.nameNode.checkpoint.transactions. So maybe you can write here, give it a value of say 500. So which would mean that if 500 transactions have been recorded in the edit file, then merge the edits with fs image. So either of these properties can be set. Otherwise, by default, this is the property of checkpointing. That is, after every 1 hour, your name node, your fs image and the edit file is merged by the checkpointing process. Okay. So this is regarding the checkpointing. Okay, I hope it's clear to all of you, right? Next, I'll discuss with you. What should I discuss? This is the most important thing now. What is checksum? So we discussed about checksum that data node it stores the actual data in itself. Plus, it also stores the checksums of the blocks, so that the blocks are not corrupted. The checksum would indicate whether the blocks are corrupted or not, and whether they should be stored in the data node or not. Okay, and these you see these Hdfs blocks are stored in files with the blk underscore prefix. Okay, this we will see in the next 5 minutes with a blk underscore prefix. So every block, the block ID starts with blk underscore, and then there is some number after that. Okay. Now, what do these blocks contain? They contain the raw bytes, okay, of the portion of the file. I hope you understand this. You have a huge file which is split up into blocks. So some part of the file is in one block, some part in another block, and so on. And these blocks have nomenclature starting with this blk underscore. Okay, and each block has an associated metadata file with the .meta suffix. Okay, so remember this, that there is a metadata file. Metadata means information about the data contained in the block. Okay, whether it is corrupted or whether it is okay. This metadata file would validate that. Okay, so we have two things when a file is split up and stored as blocks in data nodes. We have block information with information starting with blk underscore prefix, and we have a .meta file also. Okay. So this checksum file or the .meta file is made up of a header. Okay, there is a header information with version and type information. Okay. Remember this thing. There is a header information. Plus, there is a series of checksums information for sections of the block. This is important. This we are discussing how the checksum should be calculated. Okay, we can actually calculate the checksum size. Okay, so this header information is there, and this checksum information for the series of data in the block. Okay. So the .meta file will contain the checksum information for that block, which would be cross-checked when a client reads the block from the data node. If the checksum is not matched, it throws an error. Okay, fine. Then checksums are not checked if the block meta file is less than 7 bytes. Okay. This is important. Your .meta file, okay, your this .meta file is less than 7 bytes. That means your checksum is not okay. Block is corrupted, because 7 bytes is the minimum information for the header. Okay. I told you there is a header information in your checksum file, and there is some other information. This header information should be at least 7 bytes. If it is, if your block.meta file is less than 7 bytes, that means header information, version, type information is not correct. Okay, it's a corrupted block. So then checksums are not checked. Okay. And if a block and its meta file are corrupted in a certain way, the corruption can go unnoticed by a client, causing it to return invalid data. The .meta file is expected to have a header of 7 bytes, okay, and a series of other checksums. Right. So how do we calculate the checksum? Let's check. Suppose we have a file, 700 bytes. We have a block of 700 bytes. Okay. Then your header is 7 bytes. That is fixed. Now for every additional 512 bytes, listen this thing carefully. For every additional 512 bytes, 4 bytes are added to the checksum.meta file. Remember this thing. For every 512 bytes in your block, 4 bytes are added. So if I am talking of a block size of 700, what I should do? I should divide 700 by 512. I get 1.36. Okay. So 1.36 you should take it as 2. 1.06 take it as 2. So for every additional 512 bytes, 4 bytes are added. So 2 into 4, 8 bytes are there. And the size of the checksum.meta file is 15 bytes. Okay, I hope it's clear. Let's do another arithmetic with this. Let's say this is 3200 bytes. There is a block size which is 3200 bytes. So what we do here is we divide this 3200 by 512. Okay, so let's do it here. Let's look for a calculator here. Okay, we'll do it here. We have a 3200 divided by 512. So it comes up to 6.25. So you should take it as 7. Okay, I'm writing it here. This comes as 6.25. Should be taken up as 7. So it would come up to 28, and this would come up to the checksum file size would be 35 bytes. This is how checksum is calculated. Okay, and this we will see in our Hdfs cluster when we are actually storing blocks. I'll show you how this checksum would appear, whether this calculation is correct or not. Then you can check it there, right? So let's now see all these concepts that we have discussed theoretically. Let's see whether they apply in the cluster also. Okay, so I'll just close all these files, and I'll start the distributed file system services. I'm going to start with distributed file system services. That is whatever we have discussed: name node, data node, secondary name node. All these processes are there, which are doing certain functionality. Okay, so let's discuss it one by one. So I'll first discuss about the blocks. Okay, once I can see the status of my cluster as the processes are working, they're working fine. So let me list the files in my local file system, and there's a file v12. Okay, so let me list this file. So you can see this is a file of size 33 bytes. Okay, 33 bytes, right? There is another file which I don't see here. Actually, examples.desktop is a good file for our discussion. Let's see whether it's there in our cluster or not. The examples.desktop file. I'll start the web UI of our cluster and go to browse the file system. So I start my discussion from here itself. Okay. So you see there is a file examples.desktop. Okay. Its size is 8.77 KB. Okay. Let's see this information. I'll click on this file. So you see this is the block. Can you see the size? This was the same I asked in the quiz. If you are, in the poll I asked you a file of size 8980, right? This is the same file examples.desktop. So you see the block size in my cluster is 2 MB. I've kept it as 2 MB. So this examples.desktop will occupy one block only. I hope that's clear, right? The block calculation is clear. And then you see there is a block ID. There is a block ID 107374. Can you see? And then the pool to which it belongs, that is also there. Okay. So there is no BLK underscore. Can you see here? There is no BLK underscore. Okay. So while you see in the web UI, we have a block ID of the block that is stored in the data. The block ID I have highlighted, okay, and the size is here 8980. Remember, right? So I want to show you its meta file now. Okay, for that we go to data node. Okay, do you remember where the data node is? If you don't remember, say you are not remembering it, then you can do something like this. You can go to your configuration files and you can easily remember where your data node is. Okay, so I think let's go to Hdfs site file. You may find it here. Can you see the location of your name node and data node here? You set it up yourself. Okay, so it is in your file system at user local Hadoop underscore store Hdfs folder, and then there is a name node folder. So these are the locations of your name node and data node. In case you forget, you can look into this configuration file. This location has been set up by you. Okay, so I'll just close this file here, and then I'll go to my file system, local file system. Okay, and I'll go to computer. Okay, then I'll go to user. Then I go to local. Then I go to Hadoop store. Then Hdfs. Now you can see both the folders, data node and name. So I told you data node, it stores what? Block information and a .meta file which contains the checksum information, right? So open it up. Okay, there is a current folder. Open it up. There is a block pool folder. This block pool would be the same as this. Kindly check it here. Okay, ending with 0684. You can check. Okay, this is the same block pool. Okay, open it. Then again there is a current folder. Open it. Then there are two folders. One is finalized and one is replica being written. Do you remember in our when we were discussing about the concepts of blocks? Then we had this thing, a finalized sort of thing and a waiting sort of thing. So this RBW, it stands for replica being written. That is, it is not permanently stored. It is in the process of being written. And finalized means contains the blocks which are written finally. So I'll just open it. Then there is subdirectory 0. Open it. So many blocks are there. Okay. Now we need to look for R block. Let's go there. Let's look at R block. This ID is 2294. Okay. 2294. Here we have 208. Okay. Let's look for 22. It should be here at the end. Yeah. Can you see? This is our block. I've highlighted it. I think you can see. Please kindly see it clearly. 1073742294. This is our block. Okay. Let's have a look into this thing. 107374. This is our block. And can you see the associated .meta file here? So first see the block when it is stored in your data node. It is stored with the BLK underscore prefix. BLK underscore followed by the block ID. And then the same block, with its .meta file. So you just calculate it, just check whether you calculated this value only. Kindly check. All of you calculated this value, right? 79 bytes. Do you remember? This is your .meta file, the checksum file for your this particular block, that is block ending with 2294. It is indicated as BLK underscore this block number underscore some number .meta file. Okay, this is your checksum file. So I hope the process of this thing is clear. Now next what I do is, see all these blocks are there currently in your cluster. So many blocks are there. That means we are storing some big file. That is this file. Okay, I'll remove this file from there. Okay, now let's see the blocks whether they vanish immediately or slowly. Okay, see all the blocks are gone. Okay, now only two blocks are there. One is this examples.desktop, and let's see the other one. Other is your Ajay2. Okay, Ajay2 is, let's see the block number. It's 2003. Okay, let's check whether it is Ajay2. No, it's not. So again, let's have a look in our cluster which this file is. Maybe it's some older. You see, the process of deletion is not very good out here. It is time taking. So this is the block right now. Okay, I'll let it be like this. Now I'll show you how the blocks they appear here. See very carefully. So I'm suggesting that if I am storing a large file into the cluster, so many blocks would be written into your data node along with the .meta files. So blocks, first of all, they come into this folder RBW. Each block and its meta file will first come here, okay, and once it is checked that it is okay, then it goes to finalized. Okay, then it goes to finalized. So you can see in finalized right now we have just two subdirectories, okay, and then these are the two blocks and their .meta files. Only 4 entries are here in finalized right now. Okay, I hope you understood what I'm trying to suggest is that when I write something into the cluster, all the blocks will first come to RBW, okay, and immediately after checking within milliseconds, sorry, they will move to this finalized block, and once the process has completed, this RBW would be blank and this finalized block would be populated. Okay, so keep an eye on this. Now I will copy, let me copy this file, say the same Hadoop file, this file to the root of my distributed file system. Okay, I'm going to transfer it to the root. So obviously it is a big file. Let's first check the size of this file. Say ls. We can check the size. It is it's a big file. Okay, let's study it in a human readable form. So it is 578 M. Okay, so how many blocks it would be converted into? Given the block size is 2, so you divide 578 by 2. That many blocks would be written into the data. Okay, so let's write it. Let's transfer this. This command we have already discussed so many times. Put command that is used to transfer files from your local file system to the distributed file system. Right. So with this command, I transfer this file. Okay. As soon as I start the process, I will take you here into the RBW folder, and you will see the block and its meta file appearing and disappearing and going into this finalized, and maybe if the blocks are more subdirectories are created here. Okay, so you can see this process now. Okay, keep an eye on the screen. I am starting here. Okay, I take you here. I take you to RBW. You can see blocks appearing and disappearing. Now I go to finalized, I go to subdirectory 0, subdirectory 1, even subdirectory 2 has been created because 1 was full. So let's go to 2. So see the blocks are appearing here after checksum is being missed. And they were going into RBW initially. I think the process is very clear to all of you. Still the process is on. So many blocks are there, so it is just verifying and transferring to your listing. And once the process stops, you will see that RBW is blank, there's nothing in it, and all the blocks are in either subdirectory 1 or subdirectory 2. The blocks will be appearing since memory is being now we can see the blocks. So I think the process is clear to you. Okay, this was regarding our blocks, how they are placed, where they are located, what is finalized, what is replica being written. I think now it should be blank. Still the process is on. So if you look here in our browser, it would be showing that the copy is still on. Let's see. It's a big file, so a lot of checksums and all. Now it is done. Okay. So now here also it would be okay. It would be blank here also. Okay. So this was regarding this data node. Now next we discuss about FS image and edit files. Okay, so when you go to your name node folder, go to your current folder. Now you see a series of edits files and FS image files. Can you see? Ever since the cluster started, so much work has been, so many sessions have been done by me. Can you see the files? I'll list them like this. Okay, there would be a current file. Like currently, also we are working with a cluster. So there would be a current file with the name of edits in progress. Let's look for that file. Let's come currently. Okay. Can you see this file on top, all of you? This is our current edits file, which is recording the changes. Okay. Edits in progress file. Okay. We started at 10:16, right? So it is continuing, but the changes again were made when we transferred that block. So that is the edits in progress. You can see the edit files, numbers, and the dates on which they were done. So if name node is lost, if name node crashes, your FS image is destroyed, you can always pick up these things from edits file. See, all the edit file are there. And there would be FS image file also. Okay. So let's look for the FS image file. That would be there. You can just sort it by name, I think. Can you see the FS image? Okay. The FS image file. This MD5 file is a checksum file. Okay. So both these files are there. The latest FS image with checksum and edits in progress file. That is the current changes that are being recorded. So all that this you can, whatever you study theoretically in a cluster, actually that is there for you to see. It's working. So another important thing, don't do it. Even if you do it, I can tell you how to come out of it. If you just, if you just remove this file, what will happen? If you remove this file, then no update is available, and if you try to start your local host, it will say it is unable to connect. You can try it. I'll tell you how to get out of it. You just delete this file in your cluster, edits in progress. Okay. So after that, you will have problems with your name node, data node. So what should you do if you have deleted this file just for checking purpose? Okay. Then you need to again format your name node. But before you format your name node, you must remove both these folders. Remember, remove both these folders. Okay, just simply remove them from here, like right click and remove to trash, and again create these folders. After that, on your prompt, issue this command. Again, this command. The only thing is that whatever data you have would be lost. Okay, but you can recover it. Okay, so you can see the importance of edits files. That if by accidentally if you are just deleting it, then it can create problem. Edits in progress, I'm saying. Other edits you can remove. Maybe there is some problem to your cluster there. Also, you can try that. But you can always come up after that. Like if you have deleted some edits file, and if your processes are giving you trouble, you can remove both these folders so that whatever content in there that is lost, that is deleted, then again create these folders, two folders here, and then format your name node. Everything would be fine. Okay. So do try it. That's good. Okay. Now let's begin with our Hdfs command. I will discuss a few Hdfs commands today with you. Okay. And I think you are already aware of the Hadoop commands. We've already worked on a few of them. So let's have a discussion on the Hdfs commands. So the file system or the Hadoop distributed file system commands, they begin with Hadoop fs hyphen and then a command name. Okay? They begin with a hyphen. Each command in Hdfs begins with a hyphen. For example, we have just seen put, we can see list. So what is the meaning of this? That I want to list all my files from my distributed file system, the root of the distributed file system I mentioned. Okay. So you can see how many files are there. I'll show you where the files. These files are there in the root. 4 files are there, 3 files and 1 directory. Right. So let's see the output of our command. You can see the same here. Aj2, examples, Hadoop, and user. This is listed by this Hadoop fs-ls/. Or you can go an absolute, explicit reference through your Hdfs key. Okay, so you can write something like this is your name node address. Okay, and then so this refers to the root of your name node. Okay, so this will list the same thing, the same output for you, but with your explicit absolute addressing. Right? Then what if I do this? Kindly think what I'm asking. If I write this, now I'm simply saying the name node of my cluster. Okay, I'm not mentioning the root here. So when I don't mention any path, any specific path in my commands, it always goes to the default path. And you all remember that the default path in Hdfs is your user HD user folder. This is the default path in, when you don't mention any path, this is the default path. So if I list this command like this here without any default path, then it would list these two entries, .trash and C. Let's see. It will list .trash and C. Okay. So when I don't mention any path, it goes to the default path. Let's try it with a put command. Okay, I do fs hyphen put. So let me put this v12 file. That's it. I don't mention any path. I'm saying transfer this file from my local file system. The file name is v12, but I don't mention transfer it where. So you see, it will come here. It will come here in this folder. Okay. There will be another entry with the name of v2. Once I copy it here. So see, let's check whether it goes to that path. Okay. This is done. I'll refresh this so that you can see its contents. Okay. So when you don't mention any path, it goes to this path. Remember, this is a default path in HDFS. Right. And let's now go with the cat command. Okay. So there is a v12 file. Let's list its contents right now. Okay. This is v12. Then we can create another file. Okay. Say v13. Let's write this thing here. Now you see with one cat command you can display multiple files. You know this thing. Okay? So both the files, the contents are listed. And let me transfer these files. Say with this, it will prompt you because v12 is already there. Let's see what it prompts. It will say v13, no such file or directory. Okay, let's go to simple way first. There is some problem. Let's see whether okay, v13 is there. If you refresh it, you'll see v13 here also. Okay. Now I want to list the contents of both these files from this path. Okay. So I can use a cat command here also. Remember, in HDFS, cat command can only be used to display files, neither create files nor append files. That works only in your local file system. Okay. So I can write here, say v12, v13. Again, I'm not mentioning any path, so it will pick up the default path. It will display contents of both the files. Okay, I didn't mention any path. So if you want to be explicit, if you want that you would need to specify the path, then you can write like this also. Again, if I use this command, it will give you the same output. You are now explicitly specifying the path. Okay, where the files are displayed, and the same can be done for this also. Right, user HD user v13. So you understand what this both these parts, the absolute and the relative part. So this is the absolute part in this command, and this is the relative part. You see v12 we are not mentioning any part, so it means the default part, right? Okay. So cat is clear. So if you need to create, like you had a touch command, if you remember. Okay, do you remember touch command? This is used to create zero length files. Similarly, in your HDFS command, there is a touch Z command, okay, which is used to create zero length files, right? So I'm creating a Puja file using the touch Z, okay. So it will create a 0 byte file in the root with the name as Puja. So let's have a look here in our cluster. Let's go to the root. You can see the Puja file is there. You can see it here, and the size is 0 bytes. Okay. So touch Z command can help you to have 0 byte files. Okay. So next, I think that's good enough for today's session. In next session, we'll discuss a variety of HDFS commands. We'll try to finish all the HDFS commands in our next session. And meanwhile, you can just review this work that has been done, and you can ask your problems in the next session.